Hi everyone, I am Saeed. I'm the first author of this paper. Professor Danghui Wang is the corresponding author of this paper. This paper is titled as A Survey of Machine Learning and Deep Learning Based DGA Detection Techniques. This paper is submitted to the 6th International Conference on Smart Computing and Communication. In this paper, we're going to talk about cybersecurity, cyber criminals, botnet architecture, lifecycle and communication channels of botnet, domain name system, domain generation algorithm, why DGAs are difficult to detect, type of DGA detection techniques, model research challenges, and promising research opportunities. We will start with defining the main terminologies in this paper. Cybersecurity is the act of reducing risk by preventing cyber attacks on systems, networks, programs, and data from being damaged or stolen. Cyber attacks usually use something called malware. Malware is a professionally written code that runs automatically on a compromised computer without owner's consent. The cyber criminals, and sometimes they are called the adversaries, and in this paper, they are called the bootmasters, are the ones who remotely control malware to perform cyber attacks. The compromised computer or the infected computers are called in this paper as boots. Now, what is a botnet and botnet lifecycle? A botnet is a distributed network of infected devices known as boots, remotely controlled by a bootmaster to carry out a variety of harmful activities, such as sending spams, launching a distributed denial of services, email spamming, phishing, and so on. The size of botnet usually varies between a few thousand of control devices, such as Voltac, which is 80,000 boots, and millions of devices such as Fidolab, which is 30 millions of boots. The life cycle of botnet starts in propagation and ends in maintenance. Propagation refers to the spread of malware, leveraging network or system vulnerabilities, marking new boots to the botnet. Next stage is rally, which refers to the behavior of boots in receiving and getting the command and control addresses and resources. Then, after successful connection is established between the malware and the CNC server, the interaction process between them starts. The bootmasters use this CNC server to update the botnet with command and instruction that needs to be executed in the boots in specific time and domain. Also, the bootmaster use the command and control server to upgrade the malware in order to avoid the latest detection techniques and keep active all the time. The botnet architecture and communication channels. Based on the communication topology, botnet architecture are commonly categorized into three groups: centralized, distributed, and hybrid. So what is centralized? Centralized architecture is a client-server approach, which includes a CNC central control over the boots using the IRC, or the Internet Relay Chat, or HTTP. The distributed architecture is a decentralized peer-to-peer scheme. That means any node may simultaneously operate as a client and a server, where the connection process is independently processed. A botnet with a hybrid architecture has both a centralized and a decentralized architecture. So this concept is very challenging. Now we come to the communication channels. So what is communication channels? Communication channels means that the way that botnet and bootmasters communicate together. The communication channels are generally categorized into two main clusters. They are the classical and the modern command and control channels. The classic command and control channels are implemented through IRC, or Internet Relay Chat, HTTP, and peer-to-peer protocol. Modern command and control channels are divided into diversified platforms and covert communication. So covert communication means that the communication between the command and control and botnet is concealed, hidden, utilizing encryption or conversion or any information steganography. What about the diverse platforms? We here means by the diverse platform, cloud platforms, social networking sites, and blockchain. Now we comes to the domain name system or DNS. The domain name system is used to assign IP addresses to domain names and vice versa. Here we have an example. For example, if a client wants to access the google.com website, then the client type google.com in his browser. His browser sends a request to the DNS recurser, which is an internal DNS server. Then the DNS recurser calls the root level domain name server, which identifies the top level domain, which is the .com here in our example. Then the top level domain server refers to the request to the second level domain name to get the real public IP address of the website, which here is google.com. And this IP address is imaginary as 104.16.121.127. And in this way, the client can access google.com using this IP address. Now we come to a new terminology, which is called the dynamic DNS. Dynamic DNS is a method for automatically updating a name server in the domain name system. It mainly has two functions. First, the dynamic domain name system associates multiple IP addresses with a single domain name and changing out these IP addresses rapidly. This is called IP flaxing. The second function is that the dynamic DNS associates multiple domain names with a single IP address. This is called the domain flaxing, which is the main focus in our study and the main function that can be used by the attackers or bootmasters in order to communicate with the command and control servers, as we will see in the next slides. Now we come to the domain generation algorithm. What is this algorithm? The domain generation algorithm is a technique used to randomly generate a large number of domain names for a malware or a botnet command and control servers. These domain names are known as algorithmically generated domains or AGDs, which is generated based on a predefined seed value, where this seed value is shared between the malware and the attacker. DGAs are usually used by bootmasters to set up dynamic command and control channels for concealing their activities and remotely control the botnets. After generating these non-exist domain names or these random domain names, malware starts sending DNS queries for connecting to the command and control server, as we will see in the next slide. Here we have a small script of code of a generated domain name function, which use the date and time seed value. So before we will talk about the seed value. As we have said before, DGAs uses something called seed value, where this seed value is predefined and it is shared between the attacker and the malware. It is divided into two types, the static seeds and the dynamic seeds. The static seeds can be one of these, a dictionary of words, concatenation of random strings and numbers. Dynamic seeds can be one of these dynamic things, date and time, daily trending Twitter hashtag, digits of foreign exchange rate, weather temperature, and many, many others. So predicting dynamic seeds can be complex and something impossible. And in this code, you can see this code is using the year, month, and date. That means it is using the date and time dynamic seed value to generate randomly domain names using the .com domain. So now we can see in this picture how DGA works and how the malware can contact with the CNC server and get updates to perform malicious activities. In the first step, as you can see here, the attacker designed the DGA and according to a specific seed value. So as attackers knows the seed value, so he can generate the same list of AGDs in advance that malware can generate. And as you can see here, he has generated 4 domain names. The second step, attacker goes to register one of these AGDs in advance. And here, the fourth one was registered as an example. And then pointed this domain to the CNC server's address, as you can see here in step 2. In step 3 now, the malware infected boot or the malware starts now to generate AGDs. As you can see, the malware has generated the same AGDs as the attackers has previously generated because they are using the same seed value. After that, the malware starts sending queries to the DNS server to reserve the CNC server IP address. And here he started with the first IP the first domain name here, and then DNS said this domain name doesn't exist, and he tried with the second doesn't exist, the third and the fourth, and so on. And at the end or at the final step, he has found that the last domain has been registered, and the DNS server sent a response with the IP address of the CNC server. Now the malware is able to contact the CNC server and get updates to perform what is designed to do. Now we come to the why DGAs are difficult to detect. First, it is the most commonly used mechanism for current cyber attacks. Second, it depends on dynamic seed values. It is resilient to change domain names in case current domain is taken down or hinder blacklisting by network administrators. It is regularly and periodically upgraded by the bootmasters, and every day new families are developed and they burn. So what are the main type of DGA detection techniques? We have 2 types, the classical methods and the machine learning methods. The classical methods include DNS sinkhole, DNS filtering, and DNS logs and analysis. The drawbacks of these methods are they generate high noise rates, they are very computationally expensive, they don't have flexibility in detecting malicious activities. The second approach is the machine learning methods, and they are divided into 2 types: the traditional machine learning based approaches such as random forest, support vector machine, gradient boosting, Gaussian tree, and so on, and the deep learning based approaches such as RNN, LSTM, GRU, CNN, and custom TNN. The good thing about the machine learning methods, they can overcome and mitigate the classical methods drawback. As we can see here, machine learning is a subset of artificial intelligence that is capable of predicting the output accurately without being explicitly programmed. However, machine learning needs a human expert for feature engineering process to identify the best feature to study, such as the entropy, site information, linguistic, and lexical features in our DGA feature engineering. Very famous traditional machine learning algorithms are the random forest, support vector machines, k-nearest neighboring, distant trees, NiFi's, k-means, and these algorithms has been used in the last 3 years to detect DGAs. As you can see in this table summarizes the most recent DGA detection techniques proposed in the last 3 years using the traditional machine learning algorithms for only binary classification mode. As we can see in these studies, the performance is really good, but it is only considered, it has some drawbacks. As we can see here, it only considered that DNS is transparent. They don't care about encrypted DNS, which is a very high drawback. And also, they were not applied in the real time, and they are just binary classification mode. Also, a feature engineering is itself a problem, because sometimes what features that we include doesn't apply to all the DGA families. We come to the next category, which is deep learning. Deep learning is a subset of machine learning that uses artificial neural network to learn the pattern from the input data. Unlike machine learning, deep learning uses multiple layers to extract high-level features without human intervention or without any feature engineering, as it does that automatically. Also, deep learning is highly scalable, especially in the distributed computing methods. Deep learning methods also have proven their capabilities in text processing, where DGA detection is not an exception, and it is considered a text processing problem. The common deep learning algorithms that has been used in DGA detection are convolutional network, recurrent neural network, long short-term memory, and gated recurrent units. As you can see here, there are some proposed studies in the last 3 years, and as you can see here, the performance is also very good, but they are also in a binary mode, and only we have one. We have 3 ones of them. They operate in a multi-classification mode, and the last 2, they only considers 3 classes. So the accuracy of, as you can see, is a little bit good. But this one, which is the third one, the accuracy in multi-classification is only 65%. Also, we have a drawback, that is the complexity of the deep learning architecture itself, which need a very, very long time. Also, most of the deep learning algorithms, they operate sequentially, which means inputs are processed one by one. So it is a very time-consuming task. So we come to the research challenges and opportunities. As you can see here, we have 4 challenges that we still face in DGA detection. The first one is low speed rates, data imbalance sensitivity, low detection accuracy, encrypted DNS sensitivity. Low speed rates, as we all know that high speed rates are very required for real-time applications. And most of the proposed detection methods, they have a high performance in the offline environment, but when applied in the real time, it is really computationally expensive, and it doesn't have that good performance. And this because of 2 things. In deep learning, it is because of the sequential processing, which needs a very, very long time. And in machine learning, traditional machine learning techniques, it is because of feature engineering, and also because of some methods like engrams and sandbox. We have also another reason, that is botnet usually generate a very huge number of pseudo-random domain names before connecting to the corresponding command and control server. So analyzing such a very huge number of domain names is a very time-consuming job. So low speed rates is still a challenge. Here, a suggestion, maybe using some hardware accelerators or distributing the input sequence over the available GPUs might improve the accuracy and performance of the future studies. We come to the data imbalance sensitivity. Data imbalance means that the input classes are not uniformly distributed, especially in the real-time environment. As we know that in the real-world internet, the number of benign domains are much larger than the number of malicious domains, resulting in a very severe data imbalance problem that causes a huge drop in performance in real-time environments. So, considering data imbalance and handling data imbalance problems before training the model is still a challenge to the cybersecurity experts. Low detection accuracy. As we know that DGAs are constantly developing and every day new DGA families are born. And most of the proposed detection methods are built based on the known DGA families. These methods usually perform well on their various testing sets, but their performance really suffers when attempting to generalize to new DGA families or new versions of previously seen families. The last and very big challenge is that encrypted DNS sensitivity. As we know that most of the DNS servers now, the traffic is transparent. And all the previous proposed studies, they consider that the DNS traffic is unencrypted and so doesn't protect user privacy and authentication. But in fact, many very large companies such as Google and Firefox, they have already started implementing some DNS encrypted protocols such as the DNS crypt and DNS over HTTP, TLS, and DTLS. So if we have applied the previous studies on encrypted DNS sensitivity, I believe that the accuracy and the performance of this model will drop too much. We have come to an end of our presentation. And as a summary, in this presentation, we have covered the botnet detection method based on domain name algorithm. The detailed paper is published in the 6th International Conference on Smart Computing and Communication. And I would like to thank the conference organization committee and my great university, Northwestern Polytechnical University, and my professor, Danghui. Thank you so much for listening. If there is any question or doubt, please feel free to send me on my email. Thank you so much.